we are going to start spherical mirrors. In the previous lectures, we were doing plane mirrors. Now, spherical mirrors. Okay, before we start spherical mirrors, if I ask you this simple thing, how do we make plane mirrors? How do we make plane mirrors? Okay, the common mirrors. Okay, of course, the plane mirrors can be of several hundreds of types. Okay, any shiny smooth surface, if your surface is perfectly smooth and shiny, it becomes a plane mirror. Okay, but the glass, the mirror, the mirror that we use in our everyday, the normal glass mirrors, okay, how do we make it? The making is very simple. It's like this. Okay, what we do is we take a glass plate, a transparent glass plate. Okay, so this is a thin transparent glass plate. It's like this. Okay, a thin transparent plate. Okay, it does not really have to be glass. It can be any material. It has to be transparent. It should be thin. Okay. Now, what we do is we paint one side. One side is painted. It is painted. Okay. Then the other side, the light will be reflected from the other side. Okay. So if I have some light here, it is going to be reflected from this. Okay. Actually, what happens is some light enters here also. Some light will enter, but from this surface it is going to be reflected. We do see the process itself is much more complex. Okay. It is not as simple as that. Plane mirror is the simplest mirror, but the actual process happening is kind of quite involved. Okay. So here there is change in medium at this point. So some light is reflected from here. It's a transparent medium, so some light is going to enter also. Do you see this? Okay. So some light will enter, it will reach the other surface here. Then from here it will be like kind of reflected. Okay. It will come out. Okay. So that's how. Okay. But generally we ignore this thing here. We say that all of the light is reflected from this first surface itself, even though that is not actually correct. Okay. but we can approximate it like that. This painting is also known as silvering. It is also known as silvering. Okay, so whenever you hear this term in this chapter, silvering is same as painting. That's how we make a mirror, a plane mirror. How do we make a spherical mirror? Okay, we do the same process. What we do is we take a thin transparent spherical shell. Thin transparent spherical shell. Okay, so I'm taking this shell. You see, it can be made of glass. It can be made of any transparent material, plastic or any transparent material. Okay, so this is my spherical shell. Spherical shell. Now what we do is I cut it, I take out some portion of it. I cut it with a knife, let's say, or with a plane. I cut it with a plane here. So what I will get is, if I cut it, I will get a surface like this. This will be a spherical surface having same radius. Okay. So if this is the center of the original sphere. This is center of the original sphere from which I am cutting out this portion. Okay, and it has some radius. Let's say that this is the radius. Okay. This is radius. Okay, so this portion is also going to have exactly same radius. This will be center and this will be radius. Same because this thing is part of this original sphere. Okay, now let me cut out one other portion. Let me cut out like this. Okay, so I will cut out this portion here. Okay. This also is going to have its center and it is also going to have its same radius. The radius of these two portions will be any part. If I cut it like this, it is going to have same radius as the radius of this spherical shell. And then we paint it. The way I paint it here, here also I paint it. If I paint it from the outside here, then the light will be reflected from the inner surface. This kind of mirror is known as a concave mirror. A concave mirror. It is a spherical mirror, okay? Concave mirror. If I paint the inner side here, then the outer side becomes reflecting. Okay, light will be reflected from the outer side. Okay, this becomes a convex mirror. Convex mirror. Okay, concave and convex. Both are going to have same radius. You understand this? Now, this is the middle point here. This is the middle point. The middle point of this reflecting surface. Middle point of the reflecting surface for both type of mirror is known as its pole. This is its pole here. Okay. Now there are several terms associated with spherical mirrors. Okay. So we are going to first understand all those terms. In this chapter, in this lecture, we have to do a lot of things. Okay. We will try to cover the most of the theoretical part in this lecture itself. Most of the theory, or let's say all of the theory. All the theory we are going to do in this chapter, in this lecture. And if we have time, we will do few problems also. And then from the next lecture, totally problems. Okay? Okay. So try to understand it very, very carefully. Okay? Now, what are the terms associated with spherical mirrors? Terms associated with spherical mirror. Okay, the first term is center of curvature, or center. Its symbol is C. We call it center of curvature or center. What I am going to do is I am going to write all the terms. Then I will dictate and you can note down quickly. Okay, that way we can save some time. Second term is the radius of curvature. Radius of curvature, or it is only called a radius. Its symbol is R. Okay. Third term is pole. Pole is P. Okay. Fourth term is principal. Principal axis. Okay. Fifth term is a marginal range. Marginal range. Okay. Sixth term is paraxial range. Paraxial range. Okay. Then seventh term, focus. Its symbol is capital F. Okay. So we have symbol for few of these terms. Few things. Okay. Focus. Then eighth, focal length. This symbol is small f. Capital F is for focus. Focal length is small f. Okay. Then focal plane. Focal plane. And then 10th, aperture. And then 11th. 11th. It will be diameter. It is diameter. Okay, note down all the terms. Okay, I hope that it is focused well and you are able to see all of this clearly. Okay, I think that's right. Okay, now note down, I'm going to explain everything. I'm going to explain everything. Okay, you note it down. I'm not going to write everything. Okay. I will explain. In some cases, I will like tell you the definition also. Most of the times, I will be explaining. Center of curvature or center is the center of the original sphere, or let's say, no, strike off, is center of the spherical surface. That's it. Each center of the spherical surface. This is my spherical surface. Whatever is its center will be center of is known as center of curvature or simply center. So this is a spherical surface. It is going to have some center. Okay, that is known as center. That's it. It is going to have some radius. It will be same as the radius of the sphere from which it was cut. Okay. So this radius of curvature or radius of this spherical mirror will be same as the radius of the original sphere from which this was like cut out. Okay. Now, next one, pole. Note down. Middle point of the reflecting surface. Middle point of the reflecting surface. This is my reflecting surface. So middle point of it. Middle point of it. Center of it. Center of the reflecting surface. Okay. It becomes my pole. Here also, the outer side is the reflecting surface. So this middle point here is pole. Principal axis. An imaginary line or a line connecting pole and center. Note down. Principal axis. Line connecting pole and center. This is my pole. This is my center. So this line here will be principal axis of this mirror. Similarly, this line here, the line which connects center and pole, this is known as principal axis. Okay, marginal rays. Now this is something important. These two, marginal and paraxial rays, what are they? Note down, marginal rays. Light ray, parallel and away from principal axis. Light rays, parallel and away from principal axis. Okay. So if I have a light ray, this is my light ray. Okay. This light ray is parallel to this principal axis and away from it. This will become marginal ray. Marginal ray in both cases. This is my light ray. Okay. It is hitting this reflecting surface. This becomes my marginal ray. Okay. Next one, paraxial rays. Okay. Rays parallel and close. Parallel and close to principal axis. Okay. This light ray, it becomes paraxial ray. Paraxial ray here. Okay. Here also it is paraxial rays. This is my paraxial ray. It is parallel to principal axis and nearby, close. What is the significance? What is the difference between this ray here and this ray here? Note down the difference. I am going to explain it in some time. Okay. Angle of incidence. Note down. Angle of incidence for marginal rays is more than angle of incidence for paraxial rays. Or for paraxial rays, angle of incidence is very small. For paraxial rays, angle of incidence is very small. They are very close to the parallel axis. The angle of incidence is very small. Marginal rays, angle of incidence is large. Significant. Large does not mean 1000 degree. Okay. Anyway, 1000 degree makes no sense. Significant. Small. Let's say 2 degree, 3 degree, 4 degree, like that. This can be significant, 30, 40, 50, 60 degree. Okay. Now, why that happens, we will see. Focus. Focus. Note down focus. What is focus? Okay. A point on principal axis. Note down. A point on principal axis. Okay. A point on principal axis where paraxial rays meet. I am dictating it. You have to note down. I am not writing it. Okay. Today I don't want to write. I want you to listen carefully and then write down. Focus. Focus. A point on principal axis where paraxial rays meet or appear to meet after reflection from the mirror. After reflection is called focus. Okay. Noted? A point on the principal axis where paraxial rays meet or appear to meet after reflection is called focus. Okay. It is defined only for paraxial rays. Focus is not defined for marginal rays. Okay? Note down. What it means is, let's combine this thing, paraxial rays. Okay? What it means is, if I have, let's say that I have this concave mirror, this is my concave mirror, this is pole, and this is the center. Okay? This is the paraxial ray, that means a light ray which is very close to the principal axis. Okay. This light ray after reflection, okay, the point where it meets the principal axis, the point where it after reflection, this is the reflected light, this is my concave mirror, after reflection it meets the principal axis at this point here. This point is known as focus. Focus, for capital F is for focus. Okay. It is defined only for paraxial rays. Marginal rays may not meet at focus. It may pass through any point. Note this down. Only the paraxial rays will meet at focus. The marginal ray after reflection can pass through any point, not necessarily through focus. Note down, focus is defined only with regard to paraxial rays, not for marginal rays. Okay. So here they actually meet. Okay. So if I have any other paraxial ray like this is also a paraxial ray. After reflection, it will pass through center. Okay. Now, focal length, distance between focus and pole. Note down, distance between focus and pole. Distance between focus F and pole. Distance between focus and pole is called focal length. Okay, it is equal to R by 2. Note, focal length is equal to R by 2. Okay, now the next is focal plane. Okay, let's look at this focus again. So if I have this spherical, this concave mirror, then the paraxial rays will actually meet at this point here. They will actually meet. But in case of a concave mirror, convex mirror, this is my convex mirror. This side is painted, the other side becomes reflecting. Okay. So here, if I have this paraxial rays, these are paraxial rays here, one paraxial ray here, paraxial ray. After reflection, they seem to be meeting at this point. They will never meet actually. They will not meet actually, because they are going to be reflected on the same side here. So there is no chance of meeting. Okay. It's like this. Okay. So these two light rays after reflection, both are paraxial rays. After reflection, they seem to be meeting here. They seem to be diverging from this point. Okay. So this becomes focus. This distance from pole to focus, it is equal to F, and F is equal to R by 2. It is R by 2. Here also, this is pole, distance from pole and focus, this becomes F, it is equal to R by 2. This is a convex concave mirror. Okay, and this is, what is this? This is a convex mirror. Okay, Alright, now look at the behavior. What is happening to a parallel beam of light incident on this mirror, and what is happening to a parallel beam of light incident on this mirror, convex mirror. In this case, in concave mirror, the parallel beam of light converges at one point. This is the parallel beam of light. It is converging at one point here. So concave mirror is also known as converging mirror. This is because of its geometrical property. We are calling it concave mirror, and this is because of its optical property that I am calling it converging mirror. Okay, here the parallel beam of light after reflection, it is diverging. It is diverging from this point. It becomes divergent. Okay, this is known as diverging mirror. Diverging mirror. Okay, got it? So we got all of this. Now, what about focal plane? A very interesting thing. Now, if I ask you that if light rays are coming from infinity, if they are coming parallel to principal axis, okay, they are coming from infinity, okay, in that case they will meet at focus. They will converge at focus. Here they will diverge from focus. They are diverging from focus. Okay. Now, this plane, we are defining a focal plane. What is a focal plane? Note down, is a plane perpendicular to principal axis and passing through focus. Plane, note down, focal plane. Plane perpendicular to principal axis passing through focus. In same both cases, here also. This is known as focal plane. Perpendicular, this is center, perpendicular to principal axis, passing through focus. Now, what is the significance of this focal plane? Why is it important? Okay, and what it is going to be used for? It's like this. If I have a parallel beam of light, after reflection, it will converge at a point on the principal axis. It is called focus. It will diverge from a point on the principal axis. It is called focus. Both cases, same definition. Now, what will happen if I have a parallel beam of light, a parallel beam of light, but it is not parallel to principal axis. Let's say that it is incident like this. I have a beam of light which is incident like this. Okay. What will happen to this beam? Of course, they will not, after reflection, they are not going to pass through focus. Okay. So what happens is actually, after reflection, they meet at a point on the focal plane. They are going to meet somewhere here like this. Okay. This is where they are going to converge. This is focal plane. This is F and this is C. Do you see the significance of this? Now here also same things happen. Okay, if I have this parallel beam, it is not parallel to principal axis, but they are parallel anyway. Okay, it is going to be reflected like this. So this is my focus. Okay. This is my focal plane. Okay. It is going to diverge from a point on the focal plane. Okay, it is like this. Now, if I extend it backward, okay, this is how it is going to diverge. Okay. So, no, I think I'm making some mistake here. Whatever. Okay. So it is like this. So this will be diverging from this point. it will diverge something like this. Okay, so it will be diverging from a point which will be on the focal plane. Okay, this is the importance of focal plane. Now, aperture is defined variously in different books, different resources. If you try to read about this aperture, it is defined variously in different ways, in mathematical ways, or in many terms it is defined. Okay, but generally it is defined variably. Okay, but generally it is surface area. It is surface. It is area of. It is area of reflecting surface. Okay, so this is my spherical surface. This is the spherical surface. Okay, so it is a three-dimensional thing. This is not a circle. It is three-dimensional spherical surface. Okay, so I have my mirror in this form. Let's say it is in this form. Okay, this is a convex mirror. Okay, so whatever is the reflecting surface, the area of that reflecting surface is aperture. It is known as aperture. Okay, now bigger the mirror, okay, bigger is aperture. Note down, bigger the mirror. Okay, it has nothing to do with radius. Understand this. Radius. I have this mirror. It has certain aperture. Okay. Now, if I cut some part of it, try to understand. Radius remains same. Radius does not change. Okay, but now its size is reduced. We say that its aperture is reduced. Its reflecting surface is reduced. Okay, here also any mirror. If I take a smaller mirror, okay, then here also you see the radius, center, focus, pole, everything remains the same. Okay, in this case, if I cut some part from here, cut some part from here. Okay, what is the change? The size is reduced. We say that aperture has reduced. The total reflecting surface area has reduced. Aperture has reduced. Okay. Now, what is the importance of this? Okay. If the aperture is large, it will collect more light. My image will be brighter. Now, if this area is small, if the aperture is small, very small surface area, it will collect a small amount of light. Okay. Image will be dim. It will not be as bright. Okay. So that is the significance. Okay. Diameter. What is diameter? What is diameter? Okay, without any statement, let me just define it. Okay. So if I have this spherical mirror, let's say this is my concave mirror. Okay. So this distance here from end to end, this is known as diameter. Okay, it is not equal to 2r. This diameter has nothing to do with radius. Okay, of course it has to do with radius, but it is not equal to 2r. Okay, you see, this may not be 2r. What will be 2r? If I take this hemispherical circle, okay. In that case, diameter will be 2r. But generally, we take small mirrors. We never make mirrors like this. Okay, so this is diameter, end to end here. Same case goes for convex also. So this end to end distance is known as diameter. Okay, this is about the terms. Not only terms, we defined many important terms. Focus, paraxial rays, focal length, pole. Okay. Next, what we are going to do is to look at the laws of reflection. Next, we are going to look at laws of reflection. It's like this. Laws of reflection. from spherical surface, okay, are very simple, are same as those from plane surface. From plane surface, laws of the reflection remain the same, they do not change. Exactly same laws for any surface, not only plane and spherical, but any surface. Laws of reflection remain the same. Now, let's try to understand. If I have this spherical, this plane surface, okay, light is incident like this. This is how the light is incident. Okay, this is incident light. How do I find reflected light? Okay, so the point where the light is incident on this surface, I draw a normal. I draw a normal. What is the meaning of normal? Perpendicular. Perpendicular. Then I measure this angle. This is known as angle of incidence. Light will be reflected on the other side of normal, making same angle. Okay, this also is going to be same. This becomes my reflected light. All three will be in the same plane. Same thing goes for any surface. If I have a spherical mirror, let's say this is my spherical mirror. This is my spherical mirror. Okay, this is my pole. This is my center. Pole and center. This is a concave mirror, let's say. A concave mirror. Let's say that one light is incident like this. Okay. How do I find the reflected light? I will follow the same procedure. This is the point of incidence. This is the point of incidence. At this point, I will draw a normal. Drawing a normal here is easy. I just have to draw this perpendicular line. Drawing a normal here is easier. How do I draw a normal on a spherical surface? I simply join it with center. If I simply join this point with center, this line becomes normal at this point. Very simple, okay? Then this becomes angle of incidence. This is angle of incidence. Light will be reflected on the other side of normal, making same angle like this. This will be my reflected light. This is my reflected light. Okay? Now, same thing we can do it for convex mirror also. This is my convex mirror. This is pole. Let's say that this is my center. Pole and center. Focus will be in between. Okay. Now, this is a convex mirror. Let's say that light is incident like this. Okay. How do I? Okay. Let me say that this is the light. That's how the light is incident. This is my incident light. How do I draw the reflected light? Okay. Reflected light. I will follow the same procedure. Okay. First of all, I will draw a normal here. Draw normal. Drawing normal is super easy. I want to draw a normal here. Connect this point with center. It becomes normal. Okay, very easy. Okay, so you simply have to connect this thing with normal. Okay, with center. So this line becomes normal. Angle between incident light and normal is angle of incidence. Light will be reflected on the other side of normal, making same angle. Okay, it will be like this. Both angles will be same. Okay, understood? We are doing it quickly. Okay, we are trying to cover all the theories in this lecture so that we become free to solve problems only. Okay, from the next lecture. And also, these are not the things that we are doing it for the first time. The chances are, most probably, you have done these things already. Maybe some new concepts I keep on introducing in between, but most of the things you are familiar with. Okay, that is also one of the reasons that there is makes no sense like doing this slowly. Okay, so we can quickly do this. Then we will move on to the problem solving. Okay. So this is the law of reflection. Okay, now after that, some important light rays. Okay, important ray diagram. Important ray diagrams. Important ray diagrams. Okay. First, I'm just drawing the diagrams. Okay, I will explain. So I'm not going to write too many things. It is going to take time. Okay. First is like this. I have this concave mirror. Concave mirror. This is my principal axis here. This is pole. Okay. This is my center, and this is my focus. Okay. One other important thing. We discussed two types of rays, marginal and paraxial. In our syllabus, we have to study paraxial rays only. Okay. Otherwise, it is explicitly stated. Or from the problem, if you find out that this is certainly not a paraxial situation. Except those things, everything we are going to do will be for paraxial rays only. Focus is defined only for paraxial rays. So if I have a light ray which is moving parallel to this principal axis, okay, what is going to happen after reflection? It is going to pass through focus. This becomes one very important ray diagram. Okay. Now, corresponding things for this convex mirror. Okay, this is pole, and this is here I have center. This is my center here. Okay, because you see this is a imaginary line. Okay, I have a light ray which is a paraxial light ray parallel to this principal axis. This is my focus. What will happen to this light after reflection? Here, the light ray will converge at focus. Here, the light ray is going to be diverged from focus. It will diverge like this. This is the first standard case. We are going to look at few more diagrams, and that is something that you have to remember. Remember those diagrams. And that happens naturally and automatically without much effort if you solve problems. Okay. So we are going to draw a lot of diagrams. While solving problems also, we are going to draw many diagrams. Okay. When you also keep on drawing together, so simultaneously, okay, all of these things will be memorized. Now, second, this is my principal axis, and this is my center, pole, this is focus. Now understand this. Light ray, incident parallel to principal axis, after reflection passes through focus. What if I reverse it? What if I have a light ray which passes through focus? What will happen to this light? It will go parallel to the principal axis. What is this? This is reciprocity. This is reciprocity. Same thing happens here. Okay. I have this convex mirror. This is focus. This is center here. Okay. This is pole. You see, this is the reflecting surface. Okay. If a light is incident in this direction, it makes no sense. This will be garbage thing. This will be a garbage thing to even think of this. Okay. So I cannot have a light which is passing through center, which is passing through focus. I cannot have a light ray like this. Because this is the reflecting surface is here on the left, not here. Okay. So the light ray has to come from this side. Okay. Only then it will be reflected. Now what will happen if I have a light ray? If I have a light ray which appears to be heading towards the focus. So I have this light ray, it appears to be going towards the focus. What will happen after reflection? It will become parallel. This also is a case of reciprocity. Two standard diagram. Okay. Now the third one. Okay. Here I have this concave mirror. Okay, this is focus, this is pole, this is center, and this is focus. Okay, a light ray which passes. What will happen to this light? Or in case of a convex mirror, I have this convex mirror here. Okay, convex mirror. This is my pole. This is my focus. This is my center. Let's say that I have one light ray which appears to go towards the center. It appears to be going towards the center. It cannot actually reach the center, but it appears. What will happen after reflection? Now, when I draw the normal here, then it will be along this reflected light. That means this is a normal incidence. This is a normal incidence. The light ray will retrace itself. Retrace. It is a normal incidence. A normal incidence. Here also the light ray is going to retrace itself. Both cases. Now, what will happen if a light ray is along principal axis? Here, like this. A light ray is incident along the principal axis. What will happen? What will happen? Since this also is passing through the center, this is also a normal incidence, this also is going to retrace. This is also retrace. Here also, if I have a line, if I have a ray, which hits the mirror along its principal axis, then this also is going to retrace. Very important case. Now, fourth and last one. Fourth one. Okay, what is the fourth one? A light ray incident at the pole. Okay, so I have this concave mirror. This is my pole, this is my focus, this is my center. Okay, if I have a light ray which is incident like this, what is going to happen? Okay, nothing will happen. It will be reflected. If this angle is theta, this becomes the angle of incidence. So light will be reflected, making same angle on the other side. The principal axis becomes normal. Angles will be same. Got it? Okay. It will be reflected like this, making same angle. In case of convex mirror also. This is my center. This is my focus. Okay. Light is incident like this on this pole here. Okay, so this angle becomes angle of incidence. Okay, when light will be reflected on the other side, making the same angle here, this angle is theta. Okay, these are some of the important ray diagrams. Okay, now what next? Are you able to follow all of this? Are you also drawing it at the same time? Okay. Do not let me do all the things, okay, myself. I don't really want to have all the fun myself. I want you to also have some fun. Okay. So this is a ray diagram. Okay. What is the next thing in sequence? Image tracing. Okay. Image tracing. Okay, image tracing. How? Okay, we can take clues, ideas, hints from plane mirror. I have one plane mirror here, and there is one object. I want to locate its image. I want to trace its image. what do I do? We understood in the mirror, plane mirror. To trace the image, to locate image, I need minimum two light rays. Okay. So we take any two light ray, whichever you find suitable, and then look at the reflected light ray. From the reflected light ray, okay, you will be able to find the image. So let's take one incident light here, one light ray here, and the other light ray here. Any two light ray, remember. Okay. Now this is going to be reflected in this direction here, and this is going to be reflected here in this direction. These two are reflected light. They are not meeting anywhere. They are diverging light ray. But if I extend them backward here, then they appear to be diverging from this point. These two light rays, if I am standing here, these two light rays appear to me, they seem to me to be coming from this point here. This is known as image, a virtual image. Because if I go on the other side, I find nothing. The same concept, the same procedure we have to follow in spherical mirror also. Okay. So let's take one point object. Okay. Let's take this concave mirror here. I'm not like doing all this painting. Okay. The painting is like you have to understand it by default. Okay. So there is no need of doing all the painting here. We can do it without painting also, because we are doing mirror, so there is no chance of confusion here. Let's say that this is my focus. This is my focus. And this is my center. Let's say this is my center. Okay. Alright. I have an object on principal axis. Let's say that my object is here, somewhere. This is my object. On the principal axis. On principal axis. I want to find its image. I want to trace, locate its image. Where it will be. I follow the same thing. You take any two suitable light ray, whatever you find suitable. What is the most suitable one? The most suitable will be here, which goes along the principal axis. It hits the pole. This will be a normal incidence. This light will retrace. It comes out following the same one. It comes back following the same one. So this becomes reflected light corresponding to this incident light. Understand this. This is a reflected light. This is not the light which is coming from object. It is the light which is coming after reflection. Okay. Of course, there will be a light which directly comes out from the object in the same direction, but that we are not considering. Okay. Let's take any other light. Let's say this is one other incident light. I need two. How it will be reflected? So here I will draw the normal. This becomes the normal. This becomes the normal. This angle is theta. Light will be reflected on the other side, making same angle, theta. It goes in this direction. And at this point here, both reflected light meet. Do you understand this? At this point here, both reflected light meet. So this becomes the image. In this case, the light was appearing to come from this point. They were not actually coming from this point. Here, the reflected light actually meet at one point. That point is the image. This is a real image. This is known as a real image. What is the meaning of real image? If I have some screen here, if I put my hand here or any kind of screen, I will see a bright spot. I will see a bright spot. Okay? That's how images form. Now, in convex mirror, let's take case of a convex mirror here. Of course, the object has to be kept in front of the mirror because the image is formed by reflected rays. This is my focus. This is my center here. Okay? This is pole. My object is here, let's say. This is my object. This is my object. Okay? I need two light rays. Let me take this one light ray here. It is easy for me to find out the reflected light. This is the incident light. Light will be reflected in the center. This is the reflected light. I need one more. Let's take any other general random light. Let's say this is the incident light. At this point it will be reflected. I draw the normal from here. Okay, this is my normal. Normal. Okay. Now the light will be reflected on the other side, making the same angle. Making the same angle here. Now, if I have one observer here, having a very big eye, okay, this observer is going to receive these two light rays. This observer will receive these two light rays. This observer will think that these two light rays are coming from this point here. Okay, so this point becomes an image. What type of image? The light rays are not actually meeting. They just appear to be meeting. This becomes a virtual image. Two important points. Two very, very important points. First of all, image of a point object. Point object. This is a point object. Has a point image. Point object has point image. In all the cases. Point object, point image. Point object, point image. Point object, point image. First thing, note down. Point object, point image. Second thing, object on the principal axis, image is also on the principal axis. Very important point. If object is somewhere else, if object is here or here, then the image will be not on principal axis, it will be somewhere else. We will see, we will look at some problems where the object is not on principal axis, it is somewhere else. We will see how to solve it. But these 2 points you have to remember. Point object, point image, first point. Second point, object on principal axis, image also on the principal axis. Now this is for point object. What about extended objects? Extended. Okay. Let's say that I have this extended object. At the same place, okay, at the same place where I had a point object, let me put one extended object. Okay. This is my center. This is my focus here. Okay. The object was kept where? Between focus and center. Let me keep one extended object like this here. Let's say that this is my object. This is my object. Okay. So now this object has large number of points. Now I can find image of all those points separately using this method, and then I will get the image. Very tedious thing to do. Okay, what is the best thing to do here? Is not to find image of all the object, but just to find the image of one point here. Just one point. Understand this. Image of this point, I know it is going to be somewhere on principal axis. Somewhere. If I just know the image of this point, then I will join, okay, I will join the image of this point with, I will draw a perpendicular on the principal axis, I will get the image. Okay, let's see how. I just want to find the image of this point. I'm going to draw the image of this point only. Okay, forget about this whole thing. There is only one point here, that's it. Only one point. I take one standard light ray like this. What will happen? Okay, pass through focus. Parallel light passes through focus. What about this? I need minimum 2. Minimum 2. Okay. This is making some angle. After reflection, it is going to make same angle. It will be reflected like this. Here, somewhere here. Okay. What is this? This point is image of this point here. This point is image of this point. What will be image of this point? Directly below it on the principal axis. If this is A and B, then this thing is going to be B dash and this is going to be A dash. Okay. Now what is the nature of this image? The light rays are actually meeting. The reflected light rays are actually meeting here. Okay. This image is real image. This is a real image. Okay. The object is kept above principal axis. The image is below principal axis. It is called an inverted image. Inverted. This image is real. Why? Because the light rays are actually meeting. What it means? What it means is, if I keep my hand here, I will see the image on my hand. Okay? If I keep a screen here, I will get one image on the screen. And look at the size of this object. This is the size of object AB. This is the size of image. Size of image is more than size of object. We say that the image is magnified. Magnified. All of these three taken together, they are known as nature of image. Nature of image. So sometimes they ask this question, what is the nature of image? That means I have to find whether it is real or inverted or magnified. Okay, and we are going to look at the other type here. Okay, I hope that we have some time. Okay. Okay, so this is the other mirror here, the other case. Here also the object is kept similarly. Okay, this is my focus here and this is my center. Let me keep my object here. Here also I know that the image of this is going to be on the principal axis. I know it from here. I just have to find the image of this thing. That's it. I will take two standard light rays, whichever is simple for me. Let me take this one. What will happen to this? Paraxial light ray. All the cases are paraxial, because that is only the part of our syllabus. Paraxial only. Okay. Only then this will pass through focus. So this will diverge from focus. It is going to diverge from focus like this. Diverging from focus. Now, I need one more. What is one more? I can take this light here. You see, a light going towards the center. A light ray going towards the center. It will not reach center, but it is going towards it. It will retrace. It will retrace like this. Now these two are reflected light. This is reflected light, this also is reflected. So if I stand here, I will see that these two light rays are coming from this point here. Okay, so if this is my object AB, so this point is going to be image of B, is B dash, and then image of A will be directly below it, on the principal axis, A dash here, directly below it. This becomes my image. Now what is the nature of image? The reflected light rays do not actually meet. They just appear to be meeting here. They just appear. If I go behind the mirror, I see nothing. If I keep a screen here, I see nothing. Here, if I keep the screen, I will get the image, actual image. You can see it. Here I will see nothing. This is known as a virtual image. Okay, this is a virtual image. Object is kept upright above the principal axis. Image also is upright above the principal axis. We say that the image is erect. Erect. Here it was inverted. Here it is erect. Now look at the size of object, image. Smaller size. It is called diminished. Diminished. All of this was basic things about spherical mirror, basic ray diagrams, image tracing, how to locate image, how to draw the ray diagram and all that. Okay. should we do? Okay, before we wrap up, let's do two very interesting things. Should we do it? What do you think? Okay, let's do it. Let's do it, okay? It will take some time only. Then we will wrap up. In the next lecture, we are going to look at mirror formula. This I can only have an estimate. I can only locate approximately the position and nature of and the size of this image, but I cannot find the exact location. To find the exact location, to find the exact size, we need formulas. Next lecture we are going to look at formulas. We will actually derive formula, mirror formula, and then we start solving problems. Before we do that, okay, let's look at two very special cases. Special cases. Okay, special cases. Okay. Object at infinity. Where will be image? Now, if the object is at infinity, where will be image? Okay, image at focus. We will see. Now reverse it. Object at focus. Okay, image at infinity. How? This is my mirror. This is my mirror. When the object is at infinity, okay, a very large object, or at a very large distance, okay, then the light rays are going to be incident parallel to this principal axis. Okay, so if the light rays are incident like this, parallel to principal axis, in that case all of the light is going to converge here at the focus. This is my image. Object is at infinity. This is my image at focus. It will be highly diminished. This is the case when the light rays are parallel to principal axis only. Also, okay. Now here also, let's say that this is my convex mirror. Light rays are coming parallel to this. Okay, where is the image? Okay, after reflection, all of the light will be diverging from here. Okay. So when I am standing here, I will receive all the light. It appears to be coming from this point. This point is image. Now, this is nothing but reciprocity. Reciprocity. What is this? Reciprocity. Okay. If I take this as object, reciprocity, incident and reflected light can be interchanged. That means object and image can be interchanged. Now, if I keep my object here, then light rays start going in this direction. Then they will reflect in this direction. Where will be the image? At infinity. Okay. If I simply reverse this thing, okay, this was incident ray, this was reflected ray, I can interchange them. That means I can interchange the object and image also. This is something that we have to remember this, and we will do some problems where this becomes evident. That we can replace the object and image also. Okay. Here also, just simply because of reciprocity, everything is going to be reversed. Okay. Second special case. Now third special case is object at center. Object at center. Okay, in this case, this is my center, this is focus, object is also kept here at the center. Then no matter which light ray I take, all the light rays are going to retrace. Okay, all of them are going to meet at the same point. Okay, so I get image at center. Okay, so here image at center. But this happens only for concave mirror, not for the convex mirror. Not for the convex mirror. Okay, so for this convex mirror, okay, first of all, I cannot keep my object at center. It makes no sense at all. Okay, this is my center, this is my focus. Okay, can I keep my object here? Okay, it makes no sense because this is not the reflecting surface. Even if some light is incident, so that's it. End of story. Okay, now one other case is object at pole. Object at pole. What do you think if I have this spherical mirror? If object is right here, right at the pole, if object is right here, or in case of here, this is convex mirror, okay, this is pole, object is right here, close to the pole, object and pole both are at the same point, okay, image will be at pole. Image at pole. Okay. Alright, it's like this plane mirror here. I have this plane mirror. If the object is at the surface, image also is at the same point. Here also, for this object, it's very close, almost touching the pole. It's like a plane mirror for it. Okay, the image will be at the same point. This is a point which is little confusing. So you have to remember this point. Image will be at pole. Okay, so with all of this, we are ready. In the next class, we are going to kind of look at a problem and look at the mirror formula. We start doing problems based on the mirror formula from the next class.